So the first problem is dealing with a pedostatic tube or a pedo tube in this subsonic wind tunnel. So I've got air going into this tube. 150 miles per hour, 1 atmosphere. So when you see that, immediately you're going to assume standard atmosphere, right? So make sure you show the conversion here, show the lookup there, and they want you to calculate P0. Just use the definition of P0 as P plus 1/2 rho V squared. Let's see, they give you the temperature here. So again, you're going to have to convert. And so we need 1/2 rho V squared plus P. And so you're going to have to use these to calculate density using ideal gas because we don't have the density given. So the answers you should get for the density so are you guys getting that?
Did you use your ideal gas law for that?
Yeah, I use P and T. So is that what you guys got? And then you use the formula for P0. You match that. You guys should either be nodding or shaking your head because you've worked this already, right?
Okay.
Yeah. If I get the sense that people are not working the homework ahead of time, I will start spot checking, in other words, ask you to turn in a problem on the day that we go over it, just to keep you on track. You're supposed to work this, that's how you practice. All right, any questions about that?
So the pedostatic tube measures the P naught.
This is a pedo tube.
Oh, okay.
Yeah, it doesn't have a static port. Remember to measure the static pressure, you have to have a port where the flow goes like this, so then you can measure the static pressure here.
So a pedostatic tube measures the difference, while a pedo tube measures P naught?
Yeah.
Okay.
The pedostatic tube measures both, and usually you can connect them up to measure the difference.
Okay.
And that's how you can get the airspeed. Are we good on this one? Yeah. Okay, 421. Gosh, I'm lazy. All right, so you're given a pressure altitude of 8,000 feet, and when you hear that, you know that's where you're going to get your pressure. So use the tables, standard atmosphere. So that gives you the static pressure, and then it tells you that a pedo tube, so we know this. So then you use that same equation. And they're wanting us to calculate this. So we're given P, we're given P0. We need to find yeah, we don't know the density, right? They said this is pressure altitude. And they did give us the temperature, right? So again, we're going to have to use these two values to calculate the density. It's wrong to say pressure altitude is density at that 8,000 feet. You'll be close, but that's not 100% correct because it says pressure altitude. So you have to get pressure and temperature to get the density. Spot check your intermediate answer here. And then you use this formula either with sea level or the density 8,000 feet. And you should get equivalent airspeed. And then the true airspeed comes from using the actual density at those flight conditions. Again, make sure that you show your work, show your calculations, because that's what I will look for. I'm giving you the answers. So I'm not going to grade the answers, I'm going to grade you showing your work. Questions on that one? Good? And then we have a flat plate. Always draw a picture. There's the dimensions of it. Flow is coming in like this. It's sea level. So they don't give you any other information, so you can look up the density at sea level. If they told you you were at the pressure altitude of sea level, you'd have to look up pressure and then get the temperature somehow. And then get. Flatline my computer. So they want you to calculate the boundary layer thickness at the trailing edge. So you use the formula for that with x equals the trailing edge, which means you're going to have to calculate the Reynolds number. So the first thing you need to do is calculate the Reynolds number at the trailing edge, so that's here. That means you're 3 meters down the plate, like that.
They told us it was an airfoil, and that the cord length was 3.
Yeah, but you approximate it as a flat plate
Okay.
because we don't have formulas for the airfoils.
So should we draw it as a plate, or can we draw it as an airfoil?
If you want to draw it as an airfoil, that's fine. I just drew like a copy, so if you want to draw it like that, that's okay. So you calculate the Reynolds number because you know the density, you know the distance, you know the velocity, and you know the coefficient of viscosity. So spot check your Reynolds number calculation. Make sure you show it.
So we're supposed to assume it's at sea level?
Sorry, it's a call from unknown. Yeah, we have to assume it's sea level.
Okay.
So what are the units on this?
Units?
Yeah, it's a unitless, it's dimensionless parameter, so there's no units. Alright, so you use the laminar formula for delta. She did 0.00234 meters or 2.34 millimeters. Did you get that number for that? You're plugging into that formula?
I got 4.3. 2.43.
I got 234. It's 5.2 times 3 divided by 4.10 times 10 to the 7th,
I
right?
had more 6 bigs, so that's probably why.
Oh, okay. So you have 0.02334.
Yeah, so my Reynolds number is like 4.107, so
Oh, yeah, I didn't carry that out. That's all that way. So,
yeah, that makes sense.
and then the skin friction coefficient. You should get this. And that's at the trailing edge, and so that's going to give you the total drag. So you have to calculate Q infinity, 1/2 rho v squared. So you should have gotten for that 24,500. Squared is 1/2 rho. Use the density 1/2 and then the velocity of 200. So then you stick that in down here, multiply by the area, which is easy to calculate, and then CF, which is this number, and you get the total drag.
I got like a way smaller number for CF. How do you calculate CF in this case?
Let's see, the formula for that is check my calculation, did I do it right?
Probably
That's our Reynolds number, that's just the formula.
okay. I feel like
Maybe you forgot the square root.
I had like 0.664 divided by the square root of the Reynolds number. I see. I was doing the local skin friction coefficient instead of total skin friction.
Oh, yeah, okay.
That makes sense.
And it's it's because it's based on the Reynolds number at the trailing edge, so it's the whole thing. Are we good? Ask questions. This is your time to say, hey, what's going on here? Why didn't I get the right answer? And then the next problem, which is 5 instead of 4, the only difference is that you're doing turbulent instead of laminar. The Reynolds number stays the same, but these numbers change because now we're talking about turbulent. I'm going to leave these numbers up. I'm just going to lightly cross them out. So if you do the same calculation for a turbulent boundary layer, you get 0.033 meters. For the skin friction coefficient, you get 0.022. The reason I left those other numbers up is look at the difference between a laminar boundary layer and a turbulent boundary layer. 10 times as thick, even more. So turbulent boundary layer definitely is thicker, all the way down there. And look at how much drag you get. You get 10 times more drag with the turbulent boundary layer than you do the laminar. So you can see why there's a lot of work to develop airfoils that maintain the laminar boundary layer all the way down the wing. And then they discovered that it had issues with stall, and so that's why they would tailor the point where the boundary layer trips so that most of the airfoil stays laminar, but when you get down to the separation region, they trip it to turbulent to prevent the slow separation. So really, these problems are finding the right formulas, learning how to calculate Reynolds number. It's pretty much plug and crank on this stuff.
So that S is our surface area, right?
Yeah, it's the 3 times 17.5.
What are the units on our total drag? What does it look like?
Let's see, that's metric, right? So just be newtons.
Oh, so it's a force.
Yeah. And if you look at the units, it's Q infinity times S times CF, right? There's no units here. This is like meters squared, and this is newtons per meter squared. But yeah, drag is a force, lift is a force. .39 is kind of contrived. They're really just giving you a practice calculating dynamic pressure. They say if you're at 25,000 feet and you're flying at 800 feet per second, you would get, well, you have a dynamic pressure of there's your velocity. This is the density at 25,000 feet. And so you get a dynamic pressure at that altitude of 341.12. So there you just calculate the dynamic pressure from the definition. Well, they say, well, what if you're at sea level? And you have that same dynamic pressure. What velocity would you be flying at? So we're saying if you had this same number, but you were at sea level, how fast would you be going? Well, the only difference is the density here. So you look at the density at sea level and you find out that the velocity at sea level, that would give you that same dynamic pressure is 535. So what they're illustrating is that if you're at altitude, you can fly faster and you get the same dynamic pressure as a slower flight at sea level. And that has implications on lift and drag, because what it means is that at sea level, because the density is higher, you can get more energy out of the flow to produce lift. Whereas at altitude, there's less density, so there's less molecules to push on the airfoil, so you have to fly faster to get the same force, the same energy out of the air. That's really all that means. It's important, though, because they'll talk about airplanes can go faster at altitude than they can at sea level. If you measure a Mach number, it's because 2 reasons. One, the temperature goes down as you go up in altitude, so the speed for Mach 1 at altitude is lower. But the other reason is that the density is lower at altitude, so there's less dynamic pressure and you get less drag at altitude as well. So you need less thrust to go even slower and still go Mach 1 at altitude. If you go really high, you can go Mach 6, but there's hardly any air up there. And what's the speed of sound in space? Pretty close to, I mean, sound doesn't travel at all in space. The air is so rare that the temperature is pretty much absolute zero. It's really not well defined, so I'm kind of pushing the definition of speed of sound. Speed of sound is once you get really high, the speed of sound is almost close to zero. So I mean, you can be in a satellite going Mach 3 million, It just really doesn't mean anything.
So what assumptions do we need to make to use like our total drag equations and calculate our Reynolds numbers and stuff?
Those are just definitions. So
Okay.
the only assumption you make there is that, I mean, this is viscous flow, so you're not assuming inviscid or compressible or incompressible. So you're really just using the definitions in the equations.
Okay.
Yeah, so that with viscous flow, that's pretty much what you're saying is we have viscous flow and you're calculating for that.
Okay.
Yeah, I ended up, this is not a political statement, so don't worry. I watched part of the debates the other night and I got tired of that. So I switched channels and The Martian was on the movie. Have you guys seen that? I hope so, because if you haven't seen it, you need to watch it. But in that movie near the end, he takes off from Mars, the surface of Mars, in that spaceship, and they have him take the whole nose cone off, and he's essentially in a convertible with a fabric covering, right? And they can get away with that because the air density on Mars is so low that he doesn't get a lot of drag, and it's not like he was taking off from the Earth where the air coming into the space capsule would be so much it would kill him. So there's a case where the air density is a lot lower on Mars. Oh, and I recommend if you like to read books and you haven't read the book about the Martian, the book is way better than the movie, even though the movie's great. Just because it goes into a lot more details about what he does and all of that.
The audiobook is actually read by Matt Damon, the person that actually acted.
Oh, is that right? The actor? I haven't heard that, but that would be cool.
Yeah, that's pretty cool.
Yeah. All right, so we are done with chapter 4. We're going to jump to chapter 5, which is about wings and airfoils and stuff like that. So the first part of the class has been fluid dynamics. Not necessarily for airplanes, it's good for any kind of fluid flow. So that's your intro to that. And you'll get more of this when you take AE324 and 524. I think that's the right number. Arrow 1 and arrow 2. So now we're going to start talking about wings. And so to start talking about wings, we talk about airfoils because an airfoil is a cross section of a wing. So if you look at a wing, it's got this kind of elliptical, elongated shape in order to allow the flow to go smoothly around the wing. And it's also designed so that if you tilt it up, you produce lift. That's the whole reason for the wing. So we're going to draw a picture defining the geometry of that cross-section because different shapes can be defined by different numbers related to their shape. So instead of having to draw the whole shape, you'll say, well, it has this and this and this, and you know pretty much what the airfoil is. So I'm going to draw it big. And I encourage you to draw this on your notes. So the first thing you're going to do is draw a straight line all the way across. All right, got that. Now, draw the bottom edge of the airfoil as something kind of like this. This is the bottom surface, the lower surface. And then draw the top surface so that it's bigger than the bottom, so extend it up like this. That first line that you drew was the chord line, and then this distance is called the chord of the airfoil. It's really the length of the chord line. So this thing is the cord line. And the very front of the airfoil is called the leading edge. And the very tip at the end is called the trailing edge. And I'm going to start writing these things over here. So that's what I've labeled as the TE, or the leading edge. And the trailing edge is what I've labeled TE. So LE is leading edge, TE is trailing edge. And then the line from the leading edge to the trailing edge is called the cord line. And then C is the cord distance. So you either call it the cord, or most people just label it C. We use that letter C in aerodynamics to indicate that distance. So that's a measure of how long the airfoil is. All right, now draw a dotted line halfway between the upper and lower surface. Let's label those two. So this is the upper surface. This is the lower surface. Draw a dotted line halfway in between. So take this and this, an eyeball halfway in between. So we're here. If you do that all the way, you get a dotted line, because that's what I do. And this is called the mean, because it's in the middle, halfway, and that's camber. And camber is a name for how much the airfoil curves up or down.
Is that always on the upper surface?
No, if you have an airfoil that's bigger on the bottom below the cord, then it could go that way.
So it's just correlated to the bigger part?
Yeah, because I mean, imagine an airfoil that looks like this. You have to draw from whatever first meets the flow, and then you can see you'd have a mean camber line. They went like that. Turns out that it's shaped like this. If we tilt it up to produce lift that way, it has a lot of drag. It's not a good airfoil design. So most airfoils that work well have a positive camber up above.
What happens if you have a zero camber?
Then you have what's called a symmetrical airfoil. And in fact, those are real common. The top would look the same as the bottom. Right? So let's see, the mean camber line is equidistant. We're going to use this fancy word. Equidistant from upper and lower surfaces. And these are standard measures that we make of airfoils that people have standardized and say, okay, I have an airfoil that is 10 foot long and has a camber of 1 inch. And in fact, that's what we'll do is we define the camber as the maximum distance here between the cord line and the camber line. You find the maximum, and that tells you how much that's curved upward. This is called camber is equal to the max distance between the cord and the camber line. And so that's one way we define the shape of an airfoil. the distance from the upper to the lower surface is called the thickness. And of course, that varies as you move along this way, just like the camber does. So the maximum distance is what we call the max camber. We should call this max. So another way to define the airfoil is, well, how thick is it? And that's the maximum thickness as you go between the top and the bottom. We need to add that to our list. I think it's obvious what that is. It's just the maximum distance between the top and the bottom. So it's the maximum distance between the upper and lower surfaces. Okay, on time. 101. So an easy way to define what your airfoil looks at is you say it has 0 camber, which means it's symmetrical, and its maximum distance is 12% of the chord. So that tells you if this is 10 feet, then its maximum thickness is 1.2 feet. It doesn't give you all the details of the shape. I mean, you could have some weird airfoil that looks like this, right? That meets those criteria. All of that'd be weird. But we can start defining by just these numbers what the shape of the airfoil is. You know how thick it is, whether it's a thick airfoil or a thin airfoil, whether it's cambered or not. You can come up with your own way of doing this. This is just standard ways. You can say, well, my airfoil looks like my dog's face or my dog's tail, right? But then nobody knows what your dog looks like, so they go, well, what kind of airfoil is that? A bad one? Yeah. Hopefully your dog's not dead. Oh, sorry. All right, we're going to draw another picture. So in this one, draw another line across like this. We always start out easy, right? There's our line. And then you're going to draw air coming in parallel to that line. And that's our velocity, infinity. You can draw a bunch of arrows if you want because it's uniform flow. Because that's what you get when you fly your airfoil through the atmosphere. The air just sits there, but we're looking at it from an observer on the airfoil. Okay, and then draw the chord line of our airfoil here. Doing okay, we've drawn 2 straight lines and a bunch of arrows. That's the chord line. And then we're going to draw an airfoil on this. Like that. So I've drawn the airfoil tilted up. So our chord is that distance there. And this angle is called alpha. That's a really important angle because it is the angle of attack. The flow to the chord line. It's the angle of the flow to the chord line. And as you might imagine, the steeper that angle, the more force we're going to get from the air pushing up on the airfoil, just because it's tilted, right? Hold your hand out the window of your car when you're driving down the road, not too fast because blood will hit you and it'll hurt. You tilt it up, you're going to feel the force of the pressure on the bottom of your hand pushing your hand up. Right? And so we get an aerodynamic force, we'll call it F arrow.
Is that perpendicular to the chord line?
It's not in any particular direction. So if it looks perpendicular, it's not. But these directions are important. Oh, by the way, I'm drawing this at a distance 1/4 of the chord back because it turns out that's a really good place to measure the force at. All right, now this is important. These next directions you got to memorize because it's the definition. I'm going to break that vector out, force vector out, into our component perpendicular to the infinity. And I'll call that lift. This is perpendicular to the flow. And then this is the other component is drag and it's parallel to the infinity. And that is by definition. Lift is defined to be the component of the F arrow perpendicular to the infinity. And drag is the other component parallel to the infinity. And that's how we like to express vectors, right? Into two perpendicular components. So it's not perpendicular to the chord, it's not perpendicular to the horizon, it's not perpendicular to this tabletop, it's perpendicular to the flow, by definition. Okay, so why is that? Well, it's just because I said so, and everybody else says so. But the main reason is that if you have an airplane, draw a wing like this, and it's flying in cruise, so the horizon is here. The reason we need the horizon is because weight always acts perpendicular to the horizontal, right? That's just where gravity acts, it's down. So we have an airplane flying straight and level along the horizon, not on the horizon or you'd be crashing, but parallel to the horizon. Weight's perpendicular, and we define lift perpendicular to V infinity. And because we're flying straight level, V infinity is parallel to the horizontal, only because we're flying level. And so the angle alpha is that. Lift is perpendicular to V infinity, and it's going to be perpendicular to the horizon, which means it directly counteracts the weight, and then drags the other direction. So in cruise, lift is opposite, is opposing weight. So that's why we define it as perpendicular to V infinity. Now that's different if we're climbing. Lift is still perpendicular to the infinity, but weight now is still down, and those two are not directly opposing each other. And we'll talk about this condition later on. So this is, memorize right now, memorize this definition. I guarantee it'll be on the final, and it will probably be on the quiz somewhere down the road as well. So everybody say it. Lift is perpendicular to what? To the infinity, and drag is parallel to the infinity. And in cruise, it's because the drag is a drag on your desire to go forward, and the lift counteracts the weight.
So we can't say that drag is perpendicular to lift.
Oh yeah, drag is perpendicular to lift. By definition, if one's parallel and one's perpendicular. All right, the other thing that we need to talk about is that because the lift and the drag and the aerodynamic force are caused by pressure forces all over the upper and lower surfaces, these are all pressures. In statics, you guys studied distributed loads, right? That's what this is. You have a distributed load all around the upper and lower surface. And so in addition to a net force, you can get a moment from the pure. You either get a field couple or you get a distributed load. And so on airfoils, we always measure that moment about the quarter chord point. The low speed flow. So M, now we're talking about that particular point called the pitching moment. Because it pitches the airplane up or down, and it's about the quarter chord point, because people have discovered that for low speed, actually subsonic flight, this pitching moment does not change with angle of attack. And that's really nice. That means we just know this is a number, and whatever angle of attack we're flying at, that is the pitching moment we get, and we're good. And you can see that we're taking moments about this particular point, get that. And so the lift and the drag we draw acting at that point, and so changing the lift and changing the drag doesn't change the pitching moment because the moment arm is zero. Follow that? I'm drawing this aerodynamic force here. So the aerodynamic force changes with angle of attack. But because it's drawn at this point and we're taking the moments about that point, the moments don't change. F arrow does. And the people discovered this purely by experiment. Wind tunnel test, they measured lift, drag, pitching moment, and they found out, well, if you measure the pitching moments of all the pressures about this point, then that moment doesn't change, and you can just talk about lift and drag and then use the moment as a number, which makes things really nice. Now notice I emphasize subsonic flight. Remember in the video they said, well, as you get close to the speed of sound, the center of lift of the wing moves backward. And so that really happens on an airfoil. This point where the net force act starts moving backward, and at supersonic flight, it actually acts halfway back. And so that changes this pitching moment, and that's what they were talking about. When they would dive and get close to the speed of sound, the lift moved back and it would cause the airplane to pitch even more down. That's just a phenomenon of the shock waves forming on the airfoil and all of that.
So as you approach the sound, your F arrow moves closer to the sound.
Yeah. The pressure forces change if you start getting shock waves. And when you go supersonic, the whole thing is in the shock wave behind the shock wave. And it just changes the pressure forces, so the net force acts further back.
Does it ever get behind that halfway point? Go faster?
Oh, gee, I don't know. I think for supersonic flow, it's pretty much at the half point. But I don't know that much about hypersonic, so maybe if you go really fast, then it moves to a different spot. But once you go past the speed of sound, then there's shock waves coming off. And so this is all behind the shock waves, and that's why you get a different flow. There's some definitions we need to do next. But I think that's a good place to start next time. So let's call it good for today. We got a lot done. Quiz on Monday. Make sure you're ready for that. Everybody have a good weekend.
You too.